To the Occular Proteome database demonstration video. First, we're going to access the NeiCommons by typing neicommons.nei.nih.gov. Here we're taken to the NeiCommons page, and we can scroll and click this middle Occular Proteome picture, and we can explore our database. We're first greeted with an introduction page, which tells you a little bit about the purpose of the database and the methodology behind it. We can then access the database by clicking View Data. The version currently available is Profile 27-1. This database contains 90 proteins, 135 diseases, and over 970,000 mutations. The data are organized into the following 8 columns, and we can also filter our shown data using this top bar here, which filters the data shown by protein name. So if we were interested in proteins that started with the letter C, we could click this letter C, and only proteins with the C name would show. We can also filter our data by different criteria using the search bar at the top. So let's say we were interested in the proteins associated with the disease retinitis pigmentosa. So we would type this at the top here, and all proteins associated with disease would be filtered. Now, let's say we were looking to retrieve information about the protein TERP1. So we could search it at the top bar here, and we would find the entry for TERP1. The protein column here contains a hyperlinked protein. When clicked, a pop-up window arises containing a protein network. This network is interactive and shows all proteins that are known to interact with TERP1. These proteins are part of a larger network of proteins associated with inherited human disease. The distance between two nodes is smaller when they have a higher functional score, and these are more likely to interact. Proteins that are currently in the database are shown in green, while those in red have not yet been added. Each node in this pop-up can also be selected, which provides additional information about the selected node. The next column is our description column. This description includes information about the protein such as its role, mechanism of action, and family, and is most commonly retrieved from the genetics home reference. In the diseases column, hyperlinks are available for any diseases associated with mutations in this protein. Here, mutations of TERP1 have been linked to oculocutaneous albinism type 3. You can click this link, and we can obtain more information about this disease from the genetics home reference or UniProt. The in silico links column contains 4 different hyperlinks. The first is our structure image. This TERP1 image shows the ribbon structure colored by foldability. Foldability is a parameter developed by the unfolding mutation screen and is used to describe the overall destabilizing effect of missense mutations for each residue. Residues with higher foldabilities, which are colored here in red, are more likely to cause severe destabilization when mutated. By contrast, the residues in blue are more likely to have lower foldability and are more likely to cause less severe mutations. And so these points could tolerate mutations without leading to significant changes in protein stability. This image is interactive, and so we can click and zoom if we need to. This TERP1 matrix at the bottom organizes all unfolding propensities of all possible missense mutations. Here, values closer to 1 are associated with larger destabilizing effects, and any values above 0.9 are considered severe mutations. The foldability values are also shown in this matrix. There are visual representations of this unfolding matrix that was just shown as 2 different heat maps. The first is the standard heat map, and so here we see red boxes indicating high unfolding values and blue boxes representing low unfolding values. The next heat map is a clustered heat map, which clusters different rows and columns based on shared similarities. So this can be very useful since all residues which lead to higher levels of destabilization are clustered at the top, as we can see here, and residues with milder effects would be clustered near the bottom. So we can access whatever information we're interested in from this clustered heat map. And the next column, the structure column, contains two downloadable links. One is a PDB file, which contains the protein 3D structure and can be opened in programs that accept the standard PDB file format. The second file contains the 3D structure colored by foldability values, as seen in the TERP1 image under Silico links. And this file can be opened in Chimera. The number of in silico mutations provides the total number of mutations contained in the unfolding matrix and is equal to the number of residues times 20, since there are 20 possible missense mutations. The molecular modeling column contains information about how the structure was obtained. In this case, our structure was generated using homology modeling. And the column also contains values produced by our internal control, which serves as a check for quality control on the structures built using homology modeling. So a quality model should have a small p-value. Our p-value is 0.07 here, so this would be considered a model that could be improved. Finally, the UniProt ID is a hyperlink that, when clicked, will take you to the UniProt page for that given protein so we can retrieve more information if needed. Next, I want to show you guys our mutation search tool. So here we can search the unfolding effect of any specific missense mutation for any given protein. So let's say we were still interested in the protein TERP1, so we would type in our TERP1 name protein here, and we would type in some mutations that we were interested in finding. So let's say we were interested in the mutations A24T, C30R, D86, and D86Y. And these are three mutations that are experimentally known to cause the albinism disease phenotype. So if we search these three mutations, we get unfolding values here, and also a tag describing the extent of destabilization due to this mutation. In this case, all three mutations cause severe destabilization. Alright, and that is all. Thank you for watching.